Rock units follow the subduction zone, and here you may have shallow focus, devastating earthquakes, a little further down, intermediate, and then the deep focus earthquakes here. By the time the energy radiates out, it's not very destructive, and surface waves from these are minimal.
How often do those happen?
Okay, typically there are 1.3 to 1.4 million earthquakes a year.
I mean the deep focus ones.
Oh, the deep focus, they're probably only about 28% of all earthquakes. So again, they have to be along this zone. They won't form in transform plate boundaries or in divergent plate boundaries, only in this case.
Isn't that depth like
Yeah, you're getting down into the upper mantle area, you bet. Yep. And the reason it doesn't go any deeper than this would be why. Why wouldn't you expect deep focus to go beyond 700 kilometers? What? Okay, if this goes down to 900 kilometers, we won't find any earthquakes here. What's happening? What's happening to the rock units as they're going down? They're heating. They're getting closer and closer to that melting point. And rocks will only fracture when they're brittle. So you heat them up and they become almost like a thick fluid, and they're not going to exhibit earthquake phenomena. They're not going to fracture. They'll fall apart, but they're not going to fracture with any significant amount of energy release. Okay, earlier, I think last week or maybe this week, we talked about trying to determine what's on the inside of planet Earth. And they use seismic waves, earthquake waves, to determine what's inside. Now, in this particular case, if this is the focus, at this point, that's the focus, then energy is radiated out throughout this region. Now, this diagram says, well, okay, these are the paths of the energy, the earthquake waves, the P waves. If we have a uniform interior of planet Earth, if everything's the same density, the energy will travel in a straight line. Well, we know that the interior of the Earth is not uniform. So we realize that the energy waves are not going to travel in straight lines. So this has the same type of material, but dealing with different densities. And you can see now all of a sudden they begin to veer to the left and the right from the focus. But now we add different dimension to planet Earth. We're differentiating between the liquid, the solid inner core, the liquid outer core, and the mantle. And when we do this, we find out immediately that there's a big area between 103 and 103. If this is zero, your focus, you go 103 degrees this way, 103 degrees this way. All of a sudden, we have an area here which receives no earthquake data, no seismic data of a certain type. This would be the pattern for the secondary wave, the S wave. S waves go from the source area, 103 degrees in all directions, but after 103 degrees, bam, the waves are lost. So if we began to analyze what we have actually occurring, again, we start with the focal point, the earthquake focus up here, and we have the P and the S waves radiating out. Remember, we have the surface waves going along the outer edge, but the P and the S waves are being transmitted through planet Earth. Well, we still have an area between 103 and 143, which is a shadow zone. No P, no S waves. Over here, no P, no S waves. But we know that between 103 and 103, if we remember the previous photo, there are no waves at all from the secondary waves. Secondary waves do not travel through liquid. So if this is the outer core area, and it's exaggerated here as far as size, but if this is the outer core area, S waves are going to be stymied. They'll go in, they'll be absorbed, and nothing happens. The P waves, when they hit this area, they'll be refracted, but they will continue on their journey, and refraction takes place when it goes to the core of the mantle again. So the S waves are lost, the P waves are refracted, and we find that we can pick up the P waves between 143 and 143. But because of this refraction that takes place, we have shadow zones throughout this area. And geologists figured that the only way you get this pattern is to have a liquid outer core and a solid inner core. And they tried on a series of experiments, what would happen if this were smaller? Well, this pattern would change. If the inner core were larger, this pattern would change. And by taking a lot of data over a long period of time at seismic stations, they ascertained the layers of the earth. And most individuals have no problem accepting this. Now, if we look at what happens near the surface, the earthquake wave, there's your focus point. The velocity of the wave hits the asthenosphere, and all of a sudden the velocity is reduced. As you're going from a solid to a semi-solid, it's reduced, but it picks up. The materials are denser, and the waves continue on. The P wave's the same thing. When it hits the asthenosphere, it slows down. And so consequently, realizing the activity of the P and the S waves here, that's how come they were able to come up with the asthenosphere being a solid which flows, lower density, slows things down. And again, geologists were making predictions that if you get an earthquake here, you should get a P and an S wave here at a certain point. It wasn't happening. Why wasn't it happening? Because the stuff is going through the asthenosphere, slowing things down. So using this, then, geologists ended up coming up with the various focal points, coming up with the interior of the Earth, and if I get my notes back, I'll find out where I should be. Okay, we looked at folds, faults, compression. Oh, okay. Compressional referred to as tensional. Whoops, thank you. Compressional stress, tensional stress, and what is referred to as transverse stress. And that is stress where things slide past one. These three plate boundaries will develop three fault types. Now, fault is a fraction of the rock unit, displacement fraction of the rock unit. If we have tensional stress, the rock units are separated, something like this, they're pulled apart, literally ripped apart. Tensional stress will produce what are referred to as normal faults. This is what we have at the mid-oceanic ridge. The rock units are moving away from the mid-oceanic ridge. So we have normal faults. These faults produce shallow focus earthquakes. Shallow focus earthquakes. Does anybody travel between Las Vegas and Salt Lake City? Ever?